Hi guys, so in this lecture we'll be discussing about stereochemistry of cumulenes. So I have mentioned about the cumulenes in the past lectures, so I hope you remember about them. So stereochemistry of cumulenes. Stereochemistry of cumulenes. Okay. So this is a cumulene. This is the smallest cumulene and this name is alene. And if three or more carbon atoms that are directly attached with pi bonds, then it's called cumulene, and the smallest cumulene is alene. So let me write down the definition. Uh, if three or more carbons are directly attached with pi bond, then it's called cumulene, and the smallest cumulene is alene. Okay, so let's start off with the example wherein you have to match all the compounds with these groups. A is POS, then COS, C is chiral compound, D is optically active, E is chiral center, and F being C2, and let us have G also with geometrical isomerism. Okay, so you have to match the following compounds with these attributes. Okay, so let's have our first example. We have, so before that, I suppose you already have the basic understanding that if number of pi bonds are odd in cumulene, then what happens? The terminal carbon valencies are in the same plane and it will show optical isomerism. Okay, then the terminal carbon valencies are in the same plane. Okay, and if the number of pi bonds are even in cumulene, what would happen is the terminal carbon valencies would be perpendicular to each other. The terminal carbon valencies will be perpendicular to each other, and it can show optical isomerism. So if they are even, so it will not show geometrical isomerism. Okay, but it can show optical isomerism. And if they are odd, then it will not show optical isomerism. optical isomerism. Okay, so these are the 2 points you have to keep in mind. So another point, slight off topic point, is whenever you are given a cyclohexane ring and you are asked to find the symmetry in the chain form. So if you are asked to find the symmetry not in this form, but not in just inside the chair form of a cyclohexane, it can have some of substituents also attached to the chain. So then convert them into rigid form, and then you can easily answer the questions that follow. Okay, so coming back to our examples, we have this. So what would be the groups from these? So the groups would be simply, it will show there is a plane of symmetry as the number of pi bonds are even in cumulene. So the terminal carbon valencies would be perpendicular to each other. So these two H and these two H are, if they are in the same plane, then these two H will be in the Z plane, plus Z and minus Z. Okay, so it can have a plane of symmetry passing through the same plane as the compound is in. Will it have center of symmetry? No. Will it be a chiral compound? No. Will it be optically active? If it's not a chiral compound, it can't be optically active. Does it have a chiral center? No. sp2 hybridized are there. Does it have a C2? Can we rotate it across 180 degree and still the positions of atoms related to the first compound would be the same? Yes. How? You can rotate it across this with 180 degree. Okay, so A and F are the 2 attributes. Let's take a look at the second example. We have something like H here and CS3 here. Again, these two compounds are not in the same plane. These two substituents, if these two are in the same plane, then this CS3 and H would be in plus Z and minus Z. So let's see what all attributes will it carry. So is it a chiral compound? So if you see this whole cumulene as a group, then two substituents are CS3 and H above and below the plane, and these two are in the plane. So yes, it will be a chiral compound, and it will be optically active. Okay, so C is there, D is there, POS and COS are not there in this compound. You can see the reason why. There is no chiral center. This is a cumulene chiral center. There has to be sp3 hybridization. There is no geometrical isomerism here. There is no C2 here. Okay, so let me rewrite the attributes again before continuing. So A, B, C, D, E, F and G were the attributes. A was POS, B was COS, C was chiral compound, D was optically active, E was chiral center, F was C2 and G was geometrical isomer. Let's draw the structures. So we have third example as and CL here. So in this case only A would be valid. Why A would be valid? Because if these two are in the same plane as the cumulene, these two are in the opposite plane, plus Z and minus Z. So you can draw a plane which is bisecting the CS3 and H atoms into 2 and passing through this. So this plane would see that this and this are at equal distances, hence there is a POS. There is no chiral, it's not a chiral compound. It is not optically active, as it is not a chiral compound. It does not have a chiral center. It is not C2. It is not it does not have geometrical isomerism. Why? Because for geometrical isomerism the groups or substituents should be in the same plane. Okay, So next example is, if we have something like this, so will it have POS? Obviously, because there the number of pi bonds in the cumulene are odd, hence these two, all the group atoms would be in the same plane, so it would have POS. It would have COS as well. So does it have COS? Means will the compound be directly opposite to each other? So they are directly not opposite to each other, because uh, they are at far distance apart from each other, so they are not directly apart from or at equal distance from each other. Okay, so the next point is, uh, but if you draw a closer line, then you can actually see that this can be the center. It may or may not lie in the center or in the compound, but there can be a center. So just pardon me for the previous explanation. The plane of the center of symmetry can be there. And is it a chiral compound? No. Does it have C2? Yes, it will have C2. Let us look at the fifth example. We have odd number of pi bonds, so that the compound lines in the same plane. So it would have POS. Yes, it would have POS, and it would have geometrical isomerism. Okay, let's look at this example. It would not have geometrical isomerism, it would only have plane of symmetry. Okay, let us look into more examples. So if one of the pi bonds of alene is replaced by a ring, then the geometry will still remain the same. Okay, so what do I mean by that is, it's not a question, rather a star. So if one of the pi bonds of alene is replaced by a ring, then basic geometry will remain the same. Okay, so what about the chemistry of this compound, or geometry of this compound? We have this and this. So it would have, out of these matrix, which matrix will it have? It will not have plane of symmetry, center of symmetry. So if you look at it, whether this is a chiral compound or not, so if you can just see that. Okay, so these two, you can just consider this as, this is a carbon atom, and this ring would be behaving the same way as there would have been a carbon or a double bond here between two carbon atoms. So there are pi bonds between two, even number of pi bonds between the structure of cumulene. You can just consider the cyclohexane as one of the pi bonds, because the dB of a ring and a pi bond is 1. Hence, as the number of pi bonds are even, the terminal valencies would be perpendicular to each other. Now, as they are perpendicular to each other, you can see that it will surely not have geometrical isomerism, but it will surely have shortly be a chiral compound. Okay. And let us see for this case. So in this case, we have something like this. So this would be a high priority. Okay, so this is an E configuration. So it would be the number of in this case, I think I did something wrong in this case. You can consider these CS3 and H, and this H and CS3 would be in the same plane, because this carbon atom and this carbon atom are actually connected to this carbon atom, which is sp2 hybridized. Okay, so this one would be in the same plane, but these, for this CS3 and H, this would be in plus G and minus G plane, plus G are in minus G position. So not because there are the dB of the overall compound is 2, but due to the sp3 hybridization of this carbon, that is the reason these two H and CS3 would be in different plane. Okay, so the answer still remains the same, but the explanation changes. Okay, so for this compound we would have, it is having is it a chiral compound? Yes, it's a chiral compound. It is also having a chiral center. What is the chiral center? This is the chiral center. So it's having a chiral center. And is it a geometrical isomer? So if you just see that whether this is a geometrical isomer or not, so you can see that this carbon and this carbon are having different priorities, because from this side we can find a substituent at second carbon, but from this side we can find it at 1, 2, 3, 4th position. Okay, so this would actually show geometrical isomerism as well. E is there and G would also be there. And why it's a chiral center? Because of this is the chiral center. Okay, let me take the third example. Here we have, so what is the configuration it will have? It will have a E configuration when I draw H and CS3 here, because this is higher priority and this is higher priority for this. Okay, so is it a chiral compound? Yes, it would be chiral compound, because this CS3 and H would be in the same plane as this carbon atom, and this would be in the plus G and minus G. So this is a chiral center. So what was the E? So does it have a chiral center? It was a chiral compound. Does it have a chiral center? Yes, and it's also showing geometrical isomerism. Why? Because this group and this group are different, are having different priority. This is the higher priority for groups attached to this carbon atom. Okay, so let's see this example. So I'm assuming whenever the compound is a chiral, it will show optical activity. Okay, so I'm not writing that separately, but you can understand. What about this? We have CS3 here. So obviously it would have geometrical isomerism, but it is also having a POS, because if we pass the plane which is parallel to the horizontal plane, it will bisect, or it will have two CS3, one above the plane and one below the plane. So yes, it can have a plane of symmetry parallel to the horizontal plane. Okay, so it is achiral. It does not have a chiral center. Okay, and what else? Yeah, that's it. Okay, so okay, let's see the last example wherein we have this thing HCS3. So obviously this would be, if you just see the points that if you just see this carbon atom, this is actually a chiral center, so it is having a chiral center, and is it does the compound also have, is the compound having is the compound chiral? So for that thing I will leave that thing for your homework to have an answer for this question, and I hope you have an answer for this. Better you can answer directly here only that yes, it is having a chiral center and it would be a chiral compound as well. Okay, so with this we end our lecture, and in the next lecture we'll be seeing some more examples, and we'll see stereochemistry of biphenyl. Okay, so till then, good luck and goodbye.